Energy stored in a capacitor. This is a capacitor connected across a battery. This is positive terminal and negative terminal. Let V be the potential difference across the capacitor. Because of this positive potential of the battery, electrons are withdrawn from this plate. Because this positive can attract electrons, conduction electrons present in this plate. And those conduction electrons are transferred to the other plate. Since electrons are removed from this plate, it takes positive charge, and electrons are transferred to second plate means it takes negative charge. Observe, because of transfer of charge, because of transfer of electrons, charge is developed on both the plates of a capacitor, and that's because of this battery. The battery is pumping electrons from one plate to another plate. This is similar to pumping of water from ground level tank to overhead tank. If this is a house, this is tank. If this is water, then job of the pump is to lift water like this. Similarly, the battery is pumping electrons from one plate to another plate. Here, work done by the pump is stored in water as potential energy. In this case, work done by the battery in pumping the electrons is stored as energy, and that is the stored energy in capacitor. In first step, let us find out work done to transfer small charge. So it is V into dq, because V is constant. V is the applied potential difference. So what is the work done by the battery to transfer small amount of charge means this. To find out total work done, we have to integrate this equation. And this work done is the potential energy, because it is a conservative force. As a result, this work done is stored in the form of potential energy. And to solve this, let us use Q equal to CV equation. Okay. Using these two steps and this equation, we can get the final expression. Consider a capacitor of capacitance C connected across a battery such that V is the potential difference across it. Positive terminal of the battery transfer electrons from one plate to the other. Positive terminal of the battery transfer electrons from one plate to another. The work done to transfer small charge dq from one plate to another plate is dW equal to potential difference into charge. So dq is the small charge transferred. As a result, dW is the small work done. Work done to charge the capacitor by charge Q is total work done equal to integration of work done equal to integration of V into dq. Limits of integration are from 0 to 0 means uncharged capacitor to charge Q. Q equal to CV or V equal to Q by C. Therefore, work done equal to integration. In place of V, we can write Q by C into dq. Limits are from 0 to Q equal to 1 by c is constant. Take this outside. Integration of q into dq from 0 to q equal to integration of x to the power of n into dx is x to the power of n plus 1 by n plus 1. Increase the exponent by 1, write the same exponent in the denominator. Therefore, in this case, q integration of q is q square by 2. So after integration, write limits like this, 0 to q. It is q to the power of 1. 1 plus 1 is 2. That same exponent is in the denominator. Now substitute upper limit to this. 2c 1 by 2c. Substitute upper limit q square minus substitute lower limit 0, which is equal to q square by 2c. This work done is stored in the capacitor called potential energy. Stored energy is called potential energy, isn't it? Therefore, potential energy equal to half q square by c. Let us denote potential energy by U bracket. Now, different forms of potential energy. This is expression for potential energy in terms of charge and capacitance. Half q square by c, but q equal to cv implies potential energy equal to half, in place of q write cv, therefore cv its square whole square by c equal to c square v square by 2c. Or potential energy equal to half c v square. This is the expression for potential energy in terms of capacitance and potential difference. Also, in this step we have substituted for q. Now let us substitute for c. Also, c equal to q by v implies potential energy equal to q by v, in this expression half q square by q by v. Q get cancels, so it is half into q, this v goes to numerator, v. So this is the expression for potential energy in terms of q and v. Therefore, potential energy in terms of q and v, half q v. In terms of cv, half c v square. The last combination in terms of q and c, half q square by c. If sigma is surface charge density, then sigma is Q by A, or Q equal to sigma A. Second expression, capacitance of parallel plate capacitor. Capacitance of parallel plate capacitor is C equal to epsilon naught A by D. What is A? If there are two plates in a capacitor, parallel plate capacitor, then area of each plate is A, distance between the plates is D. Consider potential energy. We have expression for charge and capacitance. So let me consider potential energy U in terms of Q and C. So it is half Q square by C. Let us substitute Q and C. Q and C, these two expressions in this expression. So we get potential energy equal to half Q square. Q is sigma A its square by C is epsilon naught A by D. Equal to half sigma square by epsilon naught A square by A is A, D goes to numerator, D. So since it is sigma square by epsilon naught, imagine epsilon naught by epsilon naught here. Then the expression turns out to be sigma square, half as usual, sigma square by epsilon naught into epsilon naught is epsilon naught square. Numerator epsilon naught is there, epsilon naught. Area into length gives volume, capital V. So this is the expression for potential energy. We also know that electric field due to a conductor, charged conductor. Electric field at a point due to charged conductor is sigma by epsilon naught. Here we have sigma square by epsilon naught square. Therefore, potential energy equal to half sigma square by epsilon naught square is E square epsilon naught. Let me take this volume to the other side. Divide this by V. So what is left hand side? Potential energy by volume. So we can call it energy density. Therefore, energy density equal to potential energy by volume equal to half epsilon naught E square. This will remind us expression for kinetic energy, isn't it? Half mv square. Similarly, half epsilon naught E square. So this is the expression for energy density. Now, probable questions. Mention an expression for energy stored in a capacitor in terms of capacitance and charge. This is for 1 mark, just the expression in terms of capacitance and charge. Expression for energy in terms of capacitance and potential difference, 1 mark, capacitance and potential difference. Expression for energy in terms of charge and potential difference, again for 1 mark. Mention an expression for energy stored in a capacitor in terms of energy density in a capacitor. Energy stored in terms of energy density. Energy density is energy by volume, 1 mark. Energy in a capacitor when connected across a battery is E. E is not electric field, E is energy. Okay, it is clearly mentioned. What is the energy if applied voltage is doubled? You have to consider expression for energy in terms of capacitance and potential difference, and based on this you have to decide, 1 mark. So instead of U they have mentioned E. E stands for energy. Energy stored in a capacitor when connected across a battery is E. E is energy. What is the energy if capacitance is doubled and potential difference is halved? Capacitance is doubled, potential difference is halved means find out expression for energy E in terms of C and V and apply these two conditions. This can be asked for 1 mark or 2 mark. Similarly, this is for 1 mark or 2 mark. Mention an expression for energy density between the plates of a capacitor with the dielectric medium of constant 8. So energy density V by U by V equal to half epsilon naught E square, isn't it? But with dielectric medium, this energy density should be accompanied by epsilon R. So this is the modified equation with dielectric medium. Half epsilon naught epsilon R E square. Substitute 8 here and simplify. So energy density is 8 times because this is in the numerator. This can be asked for 1 mark or 2 marks. Derive an expression for potential energy of a capacitor. Important derivation. 3 star. Important derivation for 3 marks or 4 marks or 5 marks if all the forms are asked. Okay. Derive an expression for energy density in a capacitor. This can be for 3 marks or even for 4 marks.